In this lecture video, we want to look at our first set of calculations involving compounds, specifically calculating formula mass as well as percent composition. And so previously we discussed the mass of an atom, so we calculated the atomic mass, which we said was an average of all of the isotopes or naturally occurring isotopes, so the atomic mass, and that had units of AMU. And so it turns out we could also calculate the mass of a compound by adding up the atomic masses of all the atoms present in the compound. So just like we can determine the mass of an atom, we can determine the mass of a compound. And so this calculation, the mass of a compound, by summing up the atomic masses, is called the formula mass or formula weight. So the sum of the atomic masses of all the atoms represented in the chemical formula of a substance. And so what unit do you think this will have? Well, if you guessed AMU, you are correct. So we would sum up all the atomic masses of the atoms present in a compound to give us the formula mass. Now, you may also see the term molecular mass used for covalent or molecular compounds. And I'll say it here, but if you remember, ionic compounds like NaCl are not true compounds. So we have a crystal lattice structure, so it's not like CO2 where we'd have discrete molecules. So let's see, so if we use this to represent carbon dioxide, so we have these discrete molecules, but here we don't have, in an ionic compound, we don't have discrete molecules. Instead, we have this crystal lattice structure with alternating positive and negative ions. This is just a more specific term, molecular mass, for covalent or molecular compounds, but it wouldn't be entirely accurate to describe this term or use this term molecular mass for ionic compounds. So let's say we did have carbon dioxide, so CO2, and we wanted the formula mass, or in this case we could also say the molecular mass, since it's a covalent substance. All we would have to do is take into account how many of each atom we have present and sum up the atomic masses. So one carbon and CO2, so 12.01 plus essentially, so 12.01 times 1 plus 16 times 2 for oxygen, since we have 2 oxygen atoms present in carbon dioxide. And so from memory, I could tell you that's about 44.01 AMU. So since I used that calculation so much, but just briefly, so 12.01 times 1 plus 16 times 2. So, yep, right on the money. So 44.01 AMU. And so with that information in hand, see if you can calculate the formula mass of table salt, and then the molecular mass, which we said was essentially the same thing, but more specific to covalent substances. And so glucose has all nonmetals, so that's usually the sign that we have a covalent substance. And let's see if you can calculate the formula mass and the of sodium chloride and the molecular mass or formula mass of glucose. So pause the video, work through it, then come back. Okay, so before I go through this, I chose to watch the first part of this recording just to make sure everything was good in terms of sound, but I said something that I didn't like. I said ionic compounds are not true compounds. That is not what I intended to say. I should have said ionic compounds are not true molecules. So ionic compounds are true compounds, but they're not true molecules. And so again, this is the crystal lattice structure. And so Yeah, I had a brain slip. But yeah, so sorry if that confused you. But calculate the formula mass of table salt. So NaCl, so we have one one sodium ion times 22.998 in the formula unit of sodium chloride. Plus, and so then again, this atomic mass is going to be dependent upon how many significant figures or digits you have. Will depend on the periodic table that you're using. So on a quiz or exam, so I'll provide the periodic table, so we're using a consistent amount, but just know that depending upon the periodic table you use, there may be more or less significant figures. And so some of this I might have got from memory, and I might be inconsistent in my number of significant figures. But yeah, but depending upon the periodic table to use, significant figures, and then that will determine how many significant figures you include in your final answer. But ballpark, we should have got about 58.45 AMU. So remember units. And then next, calculate the molecular mass of glucose. So then we have 6 times 12.01 plus 12 times 1.008. And you'll use these so much that you'll probably start to remember them. And then 6 times about 16, or 15.999. And so then for memory again, that should have been about 180 AMU. So 180 AMU, and I'll just take a moment. So 6 times 12.01. And you could just fast forward through this part, but 6 times 15.999. Yes, about 180, 12, oh, 1.08. Yeah, 180.15 approximately. So hopefully you got that value. Yeah, I probably should have thought about sig figs just so to help you to train your mind to think about that. These are exact values, so 6. So here we don't consider this, so we're multiplying. So we're going to keep as many significant digits as we have here. So that would be 12.01 times 6, so 72.6. And I'm just using the values that I have, and then 12 times 1.08, so the 4 sig figs, so 12.096, and so I'm going to keep this as the last digit, but remember, try to not round for intermediate values. And then 6 times 15.999, so 95.994. So in this case, using this value, I would have 5. So 1, 2, 3, 4, 5. And so then when I add, now I'm going to looking at the value with the least number of decimal places. So looks like I should keep 2 decimal places. So 72.06 plus 12.096 plus 95.994. So yeah, so 180.15. So let's get in the habit of thinking about significant figures. Okay. So calculate the molecular mass of sulfur dioxide, a yellow-brown gas that is often associated with coal-burning power plants. So here we see that we need to know the formulas, or know how to write formulas for compounds. So everything in chemistry builds upon everything that we've learned previously. So first you need to be able to come up with the formula before you can calculate the formula mass. And then, or molecular mass. And then ammonium sulfate is a fertilizer commonly used by home gardeners. Calculate the formula mass of this compound. So pause the video, you work through it, come up with the formula, calculate the formula mass, and then come back just to make sure that you arrived at the correct answer. Okay, so then the formula for this sulfur dioxide is SO2. And then for ammonium sulfate, so we have NH4 plus and sulfate, SO4 2 minus. And so then we need to crisscross. And then that becomes NH4, 2, and then SO4. And so this 2 is distributed onto everything inside the parentheses. So hopefully you took that into consideration when calculating the formula mass. Okay, so first one, 1 times 32.07, and then plus 2 times 16.00. And if you're trying to use your calculator to plug it all in, you should use parentheses, otherwise your calculator may not interpret it correctly. So I'd use parentheses as far as possible. So this gave me 64, what I got, 64.07 AMU. And then for the next one, so we have 2 times nitrogen, which is 14.01, plus 8 times 1.008, plus 1 times 32.07 plus 4 times 16. So that should have given you about 32.15 AMU. Oh, sorry, 132.15 AMU. Okay, so your turn again. The formula weight of sodium phosphate is which of the following? Pause the video, then work through the problem, come back. So sodium is Na plus, and then phosphate is PO43 minus. So then Na3PO4. And so then you should have got about 164. So 164 should be the formula weight of sodium phosphate. And so we'll use this opportunity to put in a plug for hydrates. So a hydrate is a compound that has water incorporated into its crystals. So hydrate is a solid crystalline substance that has a certain number of water molecules as part of its structure. And so usually we have the formula of the compound, and then a dot, and then the number of water molecules that are incorporated into the crystal. If it doesn't contain water, or if it's the hydrate without water, then we call it the anhydrous form, or the anhydrous salt. So an anhydrous salt is the hydrate minus the water. And so if you're asked to calculate the formula mass of a hydrate, so all you would need to do is calculate the formula mass of the compound as usual, but then you would add, you could take the formula mass of water and then just multiply by the number of water molecules that there are. So in this case it would be 6 times 18, and so then you would just tack that on to the mass of the other part of the compound. And then finally in this lecture video, we're going to talk about percent composition. So what percent of the overall mass is due to a certain element. So we could take the molecular mass or the formula mass or the total, which we now know how to calculate. And then we take the mass that's due to that particular element. So let's say we had CO2. So take 2 times oxygen, which is about 16, divided by the total, and times 100. So this is the mass due to oxygen. So we would say 2 times 16 divided by 44.01 times 100. So about 72% of carbon dioxide is, or 72% of the mass of carbon dioxide is due to oxygen. And since there's only 2 components, we could say 100 minus that to give us the percent that's due to carbon. So they have to add up to 100%, or you could have said 1 times 12.01 divided by 44.01 times 100. So again, yeah, so about 27%. Yeah, so 27%. Okay. So determine the atomic weight of each of the element in question, or that we care about. Figure out the mass each atom contributes by multiplying the atomic mass of the atom by its subscript. Divide the number of each atom by the formula weight of the compound and multiply by 100 to get a percentage. Note you may figure out the last percentage by subtracting the other percent totals from 100. And another example, so what is the percent composition of iron 2 sulfate? So SO4 2 minus iron 2 sulfate. So we take the mass of due to iron, so 55.8 divided by the total formula mass or formula weight times 100. Then do the same for sulfur, same for oxygen, but for oxygen we multiply by 4 times 16, since we have 4 oxygen atoms. And so iron 2 sulfate is 36.7% iron, 21.1% sulfur, and 42.2% oxygen. Your turn. So metallic iron is often extracted from hematite ore composed of iron 3 oxide. What are the mass percents of iron and oxygen in iron 3 oxide? So we need to know, well, pause the video, work through this, then come back. Okay, so we need to know the formula mass of iron 3 oxide, so it might help us to know the formula of iron 3 oxide. So Fe 3 plus O2 minus, so Fe2O3. And so I'm going to cheat a little bit. So the formula mass is 159.07. And so then we would say, so for iron, so we have the percent iron would be equal to 2 times 55.85 divided by 159.7. 159.7. So that should give you about 70%. And then, so we know that since the other component is oxygen, that should give us about 30% oxygen, but you could also say 3 times that, and so sometimes it's good to double check. 159, so times 100, times 100, and so that is how we calculate percent composition.